Let us begin our discussion on database management, a fundamental topic in modern information technology. This area is essential for efficiently storing, retrieving, and organizing data in today's digital landscape. We will now explore the core pillars of relational databases, which are foundational for structured data systems. These principles guide how we organize and interact with structured information effectively. First, let's consider structured data, a key characteristic of relational databases. This means data is precisely arranged in tables, consisting of clearly defined rows and columns. Next, we have relationships, which are vital for connecting different pieces of information. Tables are linked efficiently using primary keys and foreign keys to establish connections. Moving on, SQL, or Structured Query Language, is another crucial pillar. SQL serves as the standard programming language for effective data manipulation and querying. Furthermore, ACID properties are fundamental for ensuring data reliability. These properties guarantee transaction reliability and consistent data integrity across the database. Finally, data integrity is enforced to maintain the accuracy and consistency of information. This is primarily achieved through various constraints, such as defining a primary key. Today, we are comparing relational databases with NoSQL databases, two distinct approaches to data storage. Understanding their differences is key to choosing the optimal database for your specific data requirements. Relational databases, on one side, adhere to a very structured approach. They typically feature a fixed schema and are designed primarily for structured data. These databases are known for their vertical scalability, meaning they can be scaled up. For querying and managing data, relational databases exclusively use SQL. They also strictly adhere to ACID compliance, ensuring data consistency and reliability. On the other side, NoSQL databases offer a different paradigm. They are characterized by a flexible schema, designed to handle unstructured or semi-structured data. NoSQL databases excel in horizontal scalability, distributing data across many servers. They support diverse query languages, which vary depending on the specific database type. Finally, NoSQL databases typically offer BASE consistency, prioritizing availability and partition tolerance. Let us explore the key characteristics that define NoSQL databases. These features allow NoSQL databases to adapt well to diverse and evolving data structures. First, NoSQL databases are schema-free, offering great flexibility in data organization. This means that each individual record can possess a completely different structure. Next, scalability is a hallmark of NoSQL databases, enabling growth. They achieve this by horizontally distributing data across multiple servers. High performance is another significant characteristic of NoSQL databases. They are specifically optimized for extremely fast read and write operations. Lastly, NoSQL databases support various innovative data models. These include document, key value, column family, and graph-based storage models. We will now delve into the core features that define MongoDB. These capabilities are essential for understanding its flexible approach to data handling. First, MongoDB is document-oriented, which influences how data is stored. It stores data in flexible, JSON-like documents, allowing rich data representation. These documents are then logically grouped together into collections. Another key feature is MongoDB's dynamic schema, offering immense flexibility. Documents within the same collection can indeed have widely varied structures. This means there is absolutely no need for a predefined schema before adding data. Horizontal scalability is also a fundamental aspect of MongoDB's design. This is effectively achieved through sharding, which is ideal for managing large data sets. Sharding works by distributing the data across multiple servers, enhancing capacity. Furthermore, MongoDB provides a rich query language for data retrieval. This language supports powerful operations like filtering, sorting, and aggregation. Such capabilities enable powerful queries for analyzing complex data efficiently. Let us now understand the fundamental concepts that form MongoDB. These concepts are the basic building blocks for working effectively with MongoDB. First, we have the database, which is a foundational concept. A database in MongoDB serves as a top-level container for collections. Next, we encounter the collection, a primary organizational unit. A collection in MongoDB is simply a group of related documents. Finally, we define a document, which is the most granular unit. A document is a JSON-like object containing flexible key-value pairs. We will now walk through the essential CRUD operations in MongoDB. These are the step-by-step methods for manipulating data within MongoDB collections. Here, we are inserting a single document into a collection called users. This command inserts a single document into the users collection with specified fields. Next, we are reading documents by applying a specific filter to retrieve relevant data. This command retrieves all documents from the users collection, where the age is greater than 25. Now, we will look at updating a single documents field within a collection. This command updates Alice's document in the users collection, changing her age to 26. Finally, we will demonstrate deleting a single document based on specific criteria. This command removes the document where the name is Alice from the users collection. We will now discuss the database design lifecycle, a critical process. This structured approach ensures the creation of efficient and effective databases. The first stage is requirements analysis, where we define needs. Here, we identify the database's purpose and gather all necessary user needs. Next, we move to conceptual design, which focuses on high-level structures. In this stage, we define entities, their attributes, and relationships between them. Following that is logical design, where the conceptual model is refined. We convert the ER diagrams into a detailed relational schema in this phase. The final stage is physical design, which involves implementing the database. This includes implementing storage, indexing, and optimizing queries for performance. Let us now focus on optimizing SQL queries for better performance. These are best practices that ensure efficient data retrieval and database operations. Our first best practice is to select only the required columns from your tables. Retrieving only necessary columns reduces data transfer and memory usage. It avoids unnecessary load. This query efficiently retrieves only the name and email columns from the users table, minimizing data transfer. Next, utilize the where clause effectively for filtering data. Using where filters data before aggregation, significantly reducing the workload for the database engine compared to having. This query efficiently filters products by category before counting, optimizing performance for electronics products. Another crucial practice is to limit the amount of data retrieved. The limit clause restricts the number of rows returned, which is crucial for performance when only a subset of data is needed. This query efficiently retrieves only the 10 most recent orders, limiting the data transfer. For large data sets, consider using exist instead of in. For subqueries, exist stops searching as soon as a match is found, making it more efficient than in for large subqueries as it avoids a full scan. This query efficiently finds users with orders by stopping the search immediately upon finding a match. We will now walk through setting up JPA and Hibernate in your project. This process involves integrating ORM in Spring Boot for seamless database interactions. The first step is to add the necessary JPA dependencies to your project. Include Spring Boot starter data, JPA and a database driver like H2 in pom.xml to enable JPA and Hibernate functionalities. This code snippet adds the necessary SPA and H2 database dependencies to your project's pom.xml file. Next, you need to configure your database properties within the application properties file. Set database connection details and Hibernate specific properties such as dialect and DDL auto update in application.properties. These properties configure the in-memory H2 database, setting the URL, driver, credentials, and Hibernate behavior. Finally, you will define a JPA entity, mapping your Java class to a database table. Map a Java class to a database table using JPA annotations like @entity, @table, @id, @generated value, and @column for defining fields and their constraints. This Java code defines a user entity, mapping it to a database table with ID, name, and email fields. To conclude, let us review the key takeaways from our discussion on database management. These essential concepts are crucial for understanding and implementing effective database solutions. Relational databases provide structured data storage and ensure ACID properties through SQL. NoSQL databases offer flexibility for unstructured data, excelling in horizontal scalability. MongoDB is a popular NoSQL database, featuring a document-oriented and dynamic schema. Proper database design and normalization are vital for ensuring data integrity and efficiency. Writing efficient SQL queries is essential for optimizing performance and reducing database load. ORMs like Hibernate and JPA simplify database interactions by mapping Java objects